Good morning, everyone. I hope you all had a good sleep in and you had an extra hour, so you should all be refreshed and ready for the day. Wasn't yesterday a magical? After thinking, oh, we're not going to go to Herschel Island, and then we had something I think that was just truly, truly special. So this morning I have the task of chatting to you about climate change, and I know you've all heard so much about climate change, you may be feeling a bit saturated, but hopefully I'm going to give you some really interesting stuff that you can take away with you, and also to explain a little bit about what we are seeing and what we have seen during our voyage. I think you all know me by now, even though this is the first lecture I've given. All right, good. Anyone not know me? Fantastic. Okay, so when we first started to notice climate change, it was called the greenhouse effect. And actually that's probably quite a good way of explaining it, because what it's all about is about this band of greenhouse gases that surround the Earth. And without them, life on Earth would not be possible. So effectively what they do is, as the sun sends down its solar rays, this band of greenhouse gases holds some of that, traps some of that, and it traps a lot of the long wave radiation that gets re-radiated out back from the Earth. So it's very important, and if we didn't have it, then all the heat would just be going straight back out into space. However, it's like a blanket. So in winter, if you had one blanket, it would still be maybe a bit cold. 2 blankets, it's just right. If you put a 3rd blanket on, well, then it just becomes too hot. So the concentration of greenhouse gases in this band are exactly the same as blankets. So many people say to me, oh, but there's no scientific agreement on climate change, and the scientists all disagree, and that's not true. Maybe 20, 30 years ago, there was a bit of disagreement how much of it was due to human influences, but now pretty much all scientific organizations involved with climate change, agree, and they say that observations throughout the world make it clear that climate change is occurring, and rigorous scientific research demonstrates that greenhouse gases emitted by human activities are the primary driver. And this is really a very short paragraph summing up what we know, and that's agreed on by more than 18 different scientific associations. So what do we know? Well, we know that the amount of CO2 in the atmosphere has increased dramatically since the industrial era, and we know that what we are seeing, and this you can see on the right-hand side, is very different. If you look at the light brown, the simulated human and natural influences, very different to what we would see if we only had natural influences, and I'm going to chat about those during the talk. So first of all, when are the 10 hottest years on record? Well, they've occurred in the last 24 years, and 2016 was the warmest on record, and every year close to that has been pretty much one of the hottest on records. So one of the big questions I get asked is, but what about the sun? You know, this is due to solar activity. And that is certainly something we need to look at, because solar activity has major influences on our global climate. The other influence we need to look at is what we call ENSO, which is the El Niño Southern Oscillation. And El Niño is a heating up of the sea surface temperature in the Pacific, and that's a natural cycle. So that's not caused by any human influence, but when we have an El Niño cycle, then the whole world tends to warm up. So we need to strip away any El Niño cycles if we want to see what's really going on. The other influence we need to look at is volcanoes and volcanic activities. And at the end, I'll show you how, because volcanoes spew out a lot of particulate material, that particulate material actually reflects back a lot of solar radiation. So the temperature around the globe, when there are these really massive volcanic eruptions, actually tends to cool down. So if we strip out the solar, the ENSO, and the volcanic activities, we can see that we're still on a very steep trajectory in terms of increase in global temperature. So a question that I get asked most of the time is, hasn't this happened before? And John explained very clearly, actually with really nice graphics, on how the Earth goes around the sun and the different cycles, and that it goes around, the Earth as it goes around the sun doesn't go in a circle, it goes in an ellipse. So there are times when the Earth is closer to the sun, and there are times when it's further away. Also, as John explained, the Earth wobbles on its axis. Sometimes it wobbles closer to the sun, and sometimes it wobbles a bit further away. So every time it gets much closer, then we have a warm period. When the Earth moves away from the sun in its cycle, then of course we have a cooler period. Now, if we look at proxy data, so this is data that we've taken from either ice cores, or we can look at pollens. In this case, it's looking at ice cores. We can see what the temperature was and what the composition of the atmosphere was. So what they've done is they've drilled down ice cores almost 4 kilometers deep in the Antarctic. And all of those, you've seen the ice now because you've done plenty of ice cruising. Those little air bubbles, they can extract the air, which means that they can tell exactly what the composition of the atmosphere was at the time. And using deuterium, they can work out what the temperature was. So we can see what the CO2 was and what the temperature was going back 800,000 years. And here you can see those cycles. So at the bottom, we have, in the red, we have the temperature anomalies. And at the top, we have CO2. And they look very similar, don't they? But the interesting thing is that initially, for the last 800,000 years, before the present, what was happening was, as we got closer to the sun, things started to warm up. As the Earth started to warm up, so the oceans released CO2, the permafrost started melting, they released methane. So we had an increase in CO2. With an increase in CO2, the temperature increased, and we had this positive feedback mechanism. What is happening now, however, is that CO2 is coming first. It is leading the way. So if I zoomed in on the graph, and you can see the red, that's where the temperature starts, and then the blue is where the CO2 catches up. So around 250,000 years, that's what we see. Around 125,000 years, we see that again. However, in the present, you can see that the CO2 starts. So CO2 is increasing, and the temperature is following on from that. So here we can see again how, if we put the graphs together, the CO2 is now ahead of temperature. There is this bit of anomaly in about 1940 to 1960. I'll chat about that a bit later. So we always need to say, what about the sun? Because really the sun is the big factor in our global climate. And what we found over the last 50, 60 years is that the amount of solar radiation has actually been dropping. It's been going down. So theoretically, then the temperature should be decreasing as well. But we're finding that the temperature is increasing. So that's telling us that what we're seeing now is not due to solar activity. So then we need to start saying, all right, well, maybe we need to start looking at CO2. And what we can see here is the last 1,000 years, and the CO2 level has never gone above 280 parts per million. Now, John likes putting numbers in his presentation. I don't like putting numbers in my presentations. But I want you to remember that one number, 280 parts per million. And I just want to see if I'm going to go back a little bit. Whoops. I'm going to go back to this graph, which is 800,000 years. Can you see how many times it goes above 280 parts per million? Once, when it hits about 300 parts per million. All right, so that's quite important. Because what we're at now is 418 parts per million. So we've gone up more than 35% in a concentration of gas that we know traps in heat. So it's pretty straightforward, really. And there you go. There's a just for the last 800,000 years, you can see 300 parts per million was the almost the last million years, and how we've just shot up. And this is what is so important. So there are a few take-home points, not very many, but one of them is it's not just that the climate is changing, but it's the rate of change. And this shows us very clearly that this rate of change is very, very extreme. So how do we expect global temperatures to change? So on the left, you'll see that that's just with 1.5 degrees Celsius global warming. In the middle is 2 degrees, and what would happen with 4 degrees change in global warming, and that's to the end of the century. Now, 4 degrees is pretty much the track that we're on at the moment. And the darker areas there is where the temperatures are 8 degrees plus warmer than the rest of the world. So then we need to say, well, if we're still not sure that the climate is changing, what is definitive proof that we have a changing climate? Well, it's easy. You just need to look at the clothes that people are wearing. And the fact that you were able to jump into the water way up in the Arctic tells me that that the climate is changing, because no sensible person would do anything like that. All right, a bit more seriously, how do we know the climate's changing? Well, we use 4 different indicators. We use atmospheric indicators, we use weather indicators, biophysical indicators, and economic indicators. And I'm going to talk about each of these. So first of all, atmospheric indicators. And we've seen that the amount of CO2 in the atmosphere has increased by more than 35%. Now, the thing that people don't think about is how long does that CO2 last in the atmosphere? And it stays in the atmosphere for about 100 years, which means that what we add today gets added to tomorrow and the next day and the next day, which is why we have this very steep increase, because it doesn't just go away. So even if we stopped CO2 today completely, it would still remain in the atmosphere for at least 100 years. Methane, there's been an increase of 60%, but methane has a heat carrying capacity 20 times that of CO2, so it's a very potent greenhouse gas. Nitrous oxide, a lot of vehicle emissions and industrial emissions emits nitrous oxide. We've had a 24% increase. It lasts 114 years in the atmosphere, but the problem with nitrous oxide is that it has a heat carrying capacity 100 times that of CO2. So a very, very potent greenhouse gas. And then tropospheric ozone, which is ozone in the lower atmosphere, not the ozone where we have the ozone hole. Even though it's only lasts 3 months in the atmosphere, we do need, and it's a very tiny percent, we do need to take it into account. So every ton of CO2 that we add to the atmosphere adds to global warming, because it doesn't just go away, it stays there. And by 2020, we had emitted 2,500 gigatons of CO2 into the atmosphere. Now, there is obviously a whole cycle, and a lot of the Earth takes up CO2. So maybe it doesn't matter. We need to have a look at that. So the oceans take up 1.9 gigatons per year. So they're, at the moment, a carbon sink. When the oceans start to warm up too much, they're going to start giving off a lot of carbon. The land, well, of course, our forests and trees take in CO2, but we're also cutting them down, so we have deforestation. So land uptake by new plant growth is 1.9 gigatons, but deforestation is 1.7, so they sort of equal each other out. However, we need to look at our fossil fuel burning, which emits 5.3 gigatons per year. So in total, if you do the maths, then we've got a net increase of 3.3 gigatons of CO2 per year, and that gets added on year after year. Well, what about some of our weather indicators? Well, our global average surface temperature has increased by 1.1 degrees Celsius. We know this 17 of the last 18 years were the warmest on record, with 2016 being the warmest. And to put a bit of this into perspective, I took a time series. And initially I've taken it at 50-year intervals. And then when we get closer to today, I put them in 10-year intervals. So just to give you an idea. So this is the 1890 to 1899 baseline. And where you see dark blue, it's where it's colder than the baseline. Where you see yellow or red, that's the temperature difference, where it's warmer than the baseline. So in 1884, up at the top there, you can see lots of blue, a little bit of yellow. 50 years later, 1924, pretty much blue everywhere. So it's a little bit cooler than the baseline. Jump another 50 years, 1974. Now we're starting to get less blue and more patches of yellow and red. 10 years later, and we're getting very few blue patches, and now we're starting to get patches where it's warmer, much warmer than the baseline. Another 10 years, 94, now we're getting much warmer patches again. 2004, and there's almost no blue there, so we pretty much warmer than the baseline, quite significantly warmer. And there's 2014. We haven't got to 2024 yet. Look at how the northern hemisphere is warming up much more than average. One of the important things to realize here is that with, I don't like the term global warming particularly, climate change, you can see that it's patchy. So some areas are much warmer, some areas are cooler, but it's not homogeneous. It's not the same around the world, which is why I don't like that term global warming, because it's not going to affect everyone in the same way. And if you were to plot each year, or each 10 years, each decade, you would see that each decade just gets that little bit warmer. But when you add it all up, you can see how since 1880 in the blue to, this is to June 2018, how we've had this big change. And effectively, we've just moved that whole cycle across to the side. So we really have a new climate. However, it's not a regular climate, and I'll chat about that. But basically, we're going to have more record hot weather and less cold weather. Now, if you take just one thing home with you, I want you to put this slide into your mind, because what climate change is about extremes. So it's about an increase in the duration, the intensity, the frequency, and location of extreme weather events. That's the important thing. It's about extreme events. So when you go home, read the newspaper with new eyes. Start looking at where all these extreme events are around the world. My roommate this morning was reading the news, and she said, "Oh, a tropical storm looks like it's going to hit France and Spain." Tropical storms don't normally hit France and Spain. These are the sorts of things that I want you to start looking at. But we're looking at extreme heat waves, droughts, heavy precipitation and flooding, avalanches, tornadoes, and tropical cyclones. So think about where you live and what the major weather events are. Do you live in an area where there are hurricanes? Because you're going to have more hurricanes and they're going to be more intense. If you live in an area of drought, you're going to have more droughts. So that's pretty much what you need to be thinking of. So I put in a couple of really extreme events that have happened very recently. This was in March 2022, so just a few months ago, where stations in the Antarctic were 40 degrees Celsius warmer than on average. That's just in one period. 40 degrees, that's 104 degrees Fahrenheit. That just blows my mind. It's so cold in the Antarctic that it's still below zero, only just. But if you can have one event that's 40 degrees, it's insane. It really is. So I like to use this example, even though it was quite a while back. Cast your minds back to 2003. I was at that point at the National Center for Atmospheric Research in Boulder, Colorado, and I remember very clearly during August there was this heat wave, and everyone in the northeastern part of the US was putting the air conditioners on, and that drew too much power from one power station, that tripped, and then the next one tripped, and there was a whole part of the US who didn't have power for quite a few days. On the other side of the Atlantic, in France, more than 10,000 people died of heat stress. The rivers dropped 30 centimeters in 6 days, so the barges could only carry half a load, which means that your transport prices double overnight. The water in the rivers became too warm to cool down the nuclear reactors, so they had to shut those down and buy coal-based electricity from Germany. So these are the kinds of events that we need to think about. Now, that event was that little black dot that we see there. And the red is the projections. It's a sort of a moderate, medium to high projection, which is pretty much the projection we're on at the moment. And you can see that it was a high projection. However, at the rate we're going, that's going to be a cool heat wave by 2040. Or an average heat wave, perhaps, and a really cool heat wave by 2060. We're already getting up to these levels. I've got friends who live in Dubai, and they are regularly having temperatures of 50 degree plus, and that's Celsius. Well, our body temperature is 37, so these sorts of temperatures are beyond compatible with life. So we can go into an air-conditioned room or house or building, that's fine. But what about those animals out there that simply can't cope with those sorts of heat? This was last year, 2021. How many of you live in Vancouver or Seattle, Oregon, where there was a heat dome? So you can see how, I want you to look at how this jet stream is moving. You can see how it's got these deep waves in it. And those deep waves, I'll explain to you why they're so important and how they form. But that really trapped in heat. And this was a 1 in 1,000 year event. So they had extreme temperatures there of more than, I think it was 110 or 114 degrees Fahrenheit. So these are the kinds of events we're going to be seeing. Just in 2022, this year, I know a lot of you from the UK. Did you have temperatures of 40 degree plus? 7 of the canals were closed, and the important thing is that you had 35% of the rain so far this season that you should have had. So you should have had a whole lot more. You should have had 65% more rain. And you might find that next year it goes back to normal and everyone forgets about it, but these sorts of events are going to be happening more and more frequently. Some recent heat wave deaths. Well, in Russia in 2010, there were 55,500 heat-related deaths. We don't hear about a lot of these. Pakistan, 2015, 3,700. 2021, global heat-related deaths were estimated at 356,000, and that came from the Lancet Journal. With 1.7 million deaths due to extremes, either hot or cold. Of course, when you have these hot temperatures, it means that the vegetation becomes very dry, evaporation is huge, and just a spark can set off wildfires. So California, Australia, you've all had massive wildfires, and eventually they become very, very difficult to control because they set up their own sort of atmosphere, which means that they just move extremely fast. So 2018, the wildfires in California, more than 500 square miles were burnt, 20,000 people evacuated, and they needed 14,000 firefighters. Now, I come from South Africa. We don't have 14,000 firefighters. And then, of course, the costs. We need to think of cost of $2.8 billion, which is significant. And then the US isn't just the only place that has wildfires. 2018, there were over 600 fires and 100 people killed in Spain and Portugal. And again, this year, they had wildfires. So this was August, the 11th of July to August the 7th this year, where Death Valley had flash floods. Did any of you read about this one? Yeah. Where it buried 60 vehicles, about 1,000 people were stranded. And this is another 1 in 1,000 year event. So these events are happening far more regularly. We used to think, oh, maybe a 1 in 100 year event. But no, these are 1 in 1,000 year events. What about tropical storms? Well, as the world warms up, so it heats up the sea. And as we have an increase in sea surface temperature, that fuels a lot of uplift and it fuels tropical storms. So in the blue there, we can see the sea surface temperature and we can see how that's increasing. And with it comes the power dispersion index, which is that red line that you see. And that's what's fueling these hurricanes and cyclones that we're seeing around the world. Now, on our radar is normally the Atlantic hurricanes, the ones that hit the US or the Caribbean. However, in the Pacific, they have quite just as big hurricanes there. We don't pay a lot of attention, but those are small island states that really get hit very hard. So this is a satellite image of Hurricane Patricia. It just gives you an idea of the extent of these hurricanes. And I'm going to just talk quickly about 3 main hurricanes that we had in 2017. That was Harvey, Irma, and Maria. First of all, the cost, because many people say, oh, it's too expensive for us to make changes so that we can mitigate climate change. And I say, well, what about the cost of climate change? And here we can see the cost is $282 billion. Harvey had 215 kilometer-an-hour winds and killed 107 people. Irma, 285 kilometers, 134 deaths. And if you look at the satellite images, you can see that Bermuda and St. Martin were completely destroyed, like completely devoid of vegetation after these. Perhaps the worst of the season was Maria, 280 kilometers an hour, and that caused 3,000 deaths in Puerto Rico. And it was about 8 months later, there were still areas of Puerto Rico that didn't have power. You know, we complain if our power goes out for 4 or 5 hours. Can you imagine not having power for months and months and months? So the area that I'm the most interested in is the biophysical impact. And you've probably all seen this polar bear's iconic photos sitting on a piece of ice. But it means that animals reliant on ice, such as seals and polar bears, are losing their habitat. And in the area we're traveling through, it means that a lot of polar bears are in fact coming south. And they're coming onto land, and that causes conflict between human beings and polar bears. They're also interbreeding with grizzly bears, because grizzly bears and polar bears are almost identical genetically. So it means that we're ending up with grizzly bears. It was quite interesting. I went to we had a polar bear expert on one of the voyages I was on, and he said that where you have a mother polar bear and the cub is a grizzly, the little cubs have a different sort of attitude, and they're quite, I want to say arrogant, but they need a bit of discipline by the mother polar bear, whereas the polar bear cubs, they listen to what the mom has to say. So we know that polar bears and seals are losing their habitat. We've seen very healthy polar bears, which is really good. But we've been to areas where there's been like lots of beluga whale carcasses and things. I've traveled in other areas where we've seen very, very skinny bears. Fire regime changes and wildfires, we're seeing changes in rainfall intensity. And so where you may have the same amount of rain in a season, year on year, what we're finding is that you might get most of that in 1 or 2 major rain events, which means we need to start thinking about how do we deal with our stormwater runoff. Vector-borne diseases, something like malaria, which requires certain temperature in which to live, and as the temperature, increases, it means that their sort of home range can increase. We're also seeing that there are pathogens which are jumping from one area to another and from one species to another. And then parasite infestations, such as the mountain pine beetle. So it's something we don't think about is if we have a mild winter, then a lot of the little grubs survive, which means that the next year we've got a lot more adults. And they obviously attack the plants. And what you're seeing here is avalanche peak. And where you see the red, well, those are dead trees. And that's because the winters are too mild to have that natural killing off of the pine beetle. So what about birds such as I've said Canadian geese. They don't carry passports, so you have to, I needed to go and change this. They're Canada geese. All right, they're not Canadian geese. Well, they migrate. They're quite big migrants. They need fuel or fat for migration, and they need protein for breeding. So what we're finding is that with an increase in CO2 in the atmosphere, those plants are able to assimilate that CO2, and it means that it's growing much faster. So you think, yay, that's fantastic, because there's more food for the birds, which is true. There is an increase in biomass. However, because it's growing so much faster, there's not the same amount of protein in the food. So they're not getting the protein content that they need for breeding. Then we need to say, well, as things warm up and the plants are growing much faster, there's an increase in what we call secondary plant compounds, or your tannins, which make it unpalatable and can be quite toxic to the animals. And with an increase in that growth, an increase in temperature, we have an increase in the tannins, which means that the birds are not able to eat as much. So effectively, what is happening is, even though there's more food, the protein that they're able to get and the fat that they need for migration is in fact lower, which means that in the end it has an impact in the migratory performance and breeding success of these birds. Something I find particularly interesting, and these 2 studies are done by a friend of mine called Franz Barlein, who works for the Avian Institute in Germany. And what they looked at was the breeding and the migration of birds up in the Arctic, so your Palearctic migrants. And we say, well, why do birds migrate up here? They migrate up to the Arctic because there's a lot of food. And that food comes in the form of insects. So there's this mass hatching of insects every year, which means that there's loads of food. What we're finding now with climate change is that the insects are hatching so much earlier. The birds are migrating a little bit earlier, but not early enough. So what we see on the right is, in the dark green, that's what used to be the hatching of insects. And in the black lines, that's when the birds started to arrive. So you can see most of the birds were there when there was the majority of the hatching of insects. What we're finding now is on the left, in the green, we can see that's when the insects are hatching much earlier. The birds have started migrating earlier, but not early enough so that the birds that just arrive are getting the majority of the insects, but the late arrivals are literally not getting anything. And what this means is that the birds will continue to survive. The adults will always make sure they survive, but it means that their chicks may not survive, or maybe they'll only be able to raise one chick instead of two. And this means that we'll end up having an aging bird population. So we're not going to see an immediate crash, but it means that the birds will slowly get older and die, and we'll have a decrease in the number of birds. So the high latitudes, why are they so important? Why is it so important that you are here traveling in this region at the moment? And you're really seeing the cutting edge of what's going on. Have a look at where the temperatures are the highest. They're all high up in the high latitudes, particularly up in the northern hemisphere. First of all, everyone's heard about sea ice receding, and this is just the difference between 2007 and March and 2007 September, where you can see that there's this decrease of 40% of sea ice. These are satellite images, so they don't tell you the depth of the sea ice. So we're finding more and more single-year ice, first-year ice, as opposed to the really thick ice. Now, if we're looking at the decreases, we do have cold years, because remember, it's not the same every year, it's not the same around the world. And some years we have good sea ice, and everyone goes, yay, we've got recovery. But the problem is that the general trend is down. And we've gone from 8 million square kilometers down to 4 million square kilometers. So pretty much 50% of the sea ice is no longer there. 2012 was the worst, or the lowest sea ice year, and we can see from the difference between the 1984 minimum, which is that yellow line that we get there. So my news feed came up last night with a mass carving event in Svalbard. How many of you have been to Svalbard? I know a lot of you have. All right, so it's just sort of on the other side of Greenland. And in 5 weeks, one of their big glaciers carved 800 meters. I'm trying to think of that in feet. It's a lot. So this is a time lapse. So this is from the 18th of July, and that's Svalbard. That's that little red square there is where it is. And have a look at the, you'll see where the face is. That's, as it's breaking off, that's all the sea ice. Not sea ice, sorry, the glacial ice that is carving into that bay. And that line, this line over here, has been decreasing from there to there to there. That's the 18th of August. That's the 23rd of August. So this is really a week ago. And that's the chunk that has carved off 800 meters worth in 4 or 5 weeks. It gives me goosebumps, it really does, because this is one of the things that I've read about a lot, is that we have these surges, you have these events. It's not just, oh, well, it carves a little bit all the time. And you can see all the carved ice there. So remember, I was talking about this jet stream and how it undulates, makes these very deep waves. And this is because as I'm going to go back. As the sea ice starts to decrease, well, what happens? We have a lot more warming up because the ocean is dark, it absorbs a lot more heat, and it affects the pressure cells. You don't need to know too much about it, but it means that instead of being almost a straight line that just waves a little bit, the jet stream has these huge undulations. And you can imagine, so what happens is we get a lot of cold air coming from the Arctic all the way down. And it creates these Arctic blasts that you sometimes get in the UK, or it brings really cold, snowy conditions much further south into the US. And then I get people saying, this can't be climate change. We don't have snow like this. This is really cold. No, that is climate change. That's why it's not global warming. But the same thing happens is that you have this warm air from the tropics being able to go so much further north than it would normally occur. And when we were at Holman, the guide said to me that they had temperatures of 28 degrees Celsius this year. That's bizarre. So in Fahrenheit, that's nearly 90 degrees Fahrenheit. I know that in Alaska, they've had temperatures of 30, 32 degrees, and that's because this is happening. And here you can see some areas get really cold, other areas get really warm. And this is what has caused some of the great melting events that we've had in Greenland. So what you can see is this is from 2002, how the Greenland ice mass has changed. So basically the melting off of this ice mass. And Greenland is the third biggest ice sheet in the world. Some people say the second, but actually Antarctica has 2 ice sheets. So this is then the third. If the whole of Greenland melts, well, we'd be looking at a 7-meter rise, 21-foot rise in sea level. And again, historically, we've seen that this doesn't happen slowly, it happens in surges. 2012 was one of the big events, and that was where in 4 days, you can see on the left there, the white is what was pure solid ice. The red is where there's meltwater, and you can see the whole of the Greenland ice sheet had meltwater. And this is basically what happens. Where you have meltwater, 93% of the heat gets absorbed, only 7% reflected, whereas where you have ice, then 85% of that is reflected. So that albedo is really, really important. Now, we've seen lots of polar bears. I haven't seen this behavior, but if you do, I want you, please, to just point it out to me. Just check your videos. I think we're going to have electrical points at different places for polar bears to use their razors. Now, a little bit more seriously, what are some of the changes we've seen in the far south? And I know a lot of you have been to Antarctica. And it's because the high latitudes, both north and south, are really having big impacts. What we're finding is that the peninsula, which is where we normally travel, is heating up 3 times or 4 times more than the global average. And that affects our penguin populations. We've also seen big changes in the Weddell Sea. So this is the Larsen, first Larsen A, then B, and now into the C, Larsen C ice shelf. Now, these ice shelves are not going to affect, the breaking up of these are not going to affect sea level rise, because their weight is already taken up by the ocean. What it does do, though, is it slows down the move of continental ice by 3 to 4 times. So if we lose them, it means our continental ice is moving into the ocean much faster. We've seen big changes in penguin populations. Adelie penguins, the numbers since 1974 have decreased by more than 90% in one of their study sites. Gentoo penguins are doing much better. Chinstrap penguins across the peninsula have declined by 50%. And that's not related to tourism or anything like that. Part of the reason for this is because it's now warm enough to snow and to rain. So the birds start their nesting, and then they get covered with 1.5 meters of snow. They have to abandon the eggs, and they don't relay. The Gentoo penguins will relay their eggs, so that's why they're a bit better adapted. How many of you have been here? This is South Georgia. There are a few of you, all right. South Georgia is the most amazing place on the planet. All right. If you're going to book a trip anywhere, book one to South Georgia. It really is, and I can tell you about it. But South Georgia really is. It's just a stupendous place. And you do that on the way to Antarctica. And in 2009, when we went there, we came across really like almost a mass die-off of first seal pups. We went to a colony of Gentoo penguins where we found out later that the count had gone from 1,800 pairs the following year to 124. And the reason for this was that warm water moved south of South Georgia, and with that moves all the krill, because krill can survive in 4-degree centigrade water, and it meant that it was out of the range of the feeding of these penguins. Subsequent years, it's warmed, it's cooled down again. We've had good krill years. The birds have been able to re-establish. But if we have these sorts of events year on year, it will affect the populations. Everyone talks about sea level rise. Well, Antarctica is not going to melt completely in the near future. However, Greenland at 7 meters will have a big influence. That also, Greenland's not going to melt completely in a few years, but what we've started will continue. In terms of economic impact, and a lot of you may still be in business or you have investments, and it's something to think about. And I always think if you want to know what the impacts are, who better to speak to than someone in the insurance business? And Lloyd's of London already in 2006 said that failure to take climate change into account will put companies at risk from future legal actions from their own shareholders, their investors and clients. Climate change must inform underwriting strategy from the pricing of risk to the wording of policies. It must guide and counsel business strategy, including business development and planning. So if you do have investments, have a look at their, at how what their climate change plans are. Even if they're not doing anything about mitigation, what are their potential risks in the areas that they operate? Because the cost of extreme weather events is increasing. This shows 2005 at $200 billion of overall insured losses due to weather events. This is from 1950. But that pales into insignificance if you just look at the 2017 hurricanes. Just those 3 hurricanes cost $282 billion. That's excluding all the other major events around the world. So the cost of these major extreme weather events is increasing. Now I'm going to show you an animation of the global temperature as it's from, I think it's 1870. At the bottom, you'll see the impact of different volcanic eruptions and how it actually cools the world down. As we move further, it will then move from what we've seen onto the projections. And you can see what the world will look like at our current rate up until 2100. Now, of course, the world doesn't end at the end of the century. We're going to continue. And in the middle there, on the right, you can see the year, 1876, and the temperature relative to the 1870-1899 baseline. Krakatoa happens, and it actually cools down by a couple of degrees for a period of 4 or 5 years. Santa Maria, the next big eruption. So the colors that we're seeing are still sort of blue, still cooler than the baseline. Now we're going 0.1 degrees Celsius. And we have this little blip around 1940, 1950. And this was due to an increase in solar radiation that we had during that time. Also, there hadn't been any major volcanic eruptions for a long period. Now we're coming up to 1980. We had a couple of quite big eruptions. There's Pinatubo. Have a look now at the high latitudes in the north. It's getting much, much warmer. We're now at 1.5 degrees increase from the baseline. Now we're looking at our projections, and we're at 2040. That's 2.2 degrees. And you can see how patchy it is, where the high latitudes are already at this point about 8 degrees Celsius warmer than the average. If we carry on going 2080, that's 3 degrees. That's what 3 degrees will look like. And right to the end of the century. So we're not going to be around, but our grandchildren or great-grandchildren, they'll be having to deal with these temperatures. But I say global warming, it's not actually about temperatures, it's about these very extreme events. So how do we need to address climate change? First of all, climate change is happening, whether we want to believe it or not, and we have to take a two-pronged approach. The first is that we have to mitigate, so we have to reduce our CO2. Whether we like it or not, we have to start changing the way we think, the way we do things. And I'm a pragmatist. I don't believe that, we're all going to stop CO2 emissions today and, go and live in mud huts. But we need to start making intelligent decisions. We also need to adapt. So we have to we have to understand climate change, and this lecture is perhaps the first step in understanding how it's going to affect you and how you personally can start adapting to it, making sure that you're ready for it. So some of the things that you can do, I always think, well, we mustn't think just of CO2, we must think of waste and pollution, because they're intricately linked. I like to think, how much fuel does your car use, and what is the amount of CO2 that you're producing by driving your car? Now, again, I'm from South Africa. We don't really have good public transport. Where I live outside of town. I have to use a car. So I think, I need to go and buy bread, which is 8 kilometers away. So I drive my 8 kilometers there and 8 kilometers back. Well, I've just emitted 2 kilograms of CO2 to go and buy that loaf of bread. So let's start thinking about, maybe we don't need to travel, or we can combine our travel. Because 7.7 kilometers is 1 kilogram of CO2, or 2.3 miles is equal to 1 pound of CO2. And that's for an average car. So that's an average car emits 130 grams of CO2 per kilometer. If you're driving a really big car, of course, you're going to be emitting a whole lot more. So we're not all going to stop driving cars, but if you're going to buy a new car, well, then think of buying a hybrid, or buying a car that has very low fuel consumption, or even an electric vehicle. And there's a lot of people will have a lot of things to say about electric vehicles. I'm not going to get into that discussion now, but it certainly is more efficient. What about your energy use? Well, this is taken from Australia. If you were to, for every kilowatt hour, you would be emitting 656 grams of CO2. So if you boiled a kettle for 30 minutes, that would be the equivalent of releasing 1 kilogram of CO2. Now, if we start to work out what our energy consumption is, and from that what our CO2 emissions are, it might make us a little bit more motivated to make intelligent choices. And that's really what I want you to think about. Maybe you should buy local instead of buying those bananas that have been imported from Ecuador. Think of buying fruit and vegetables that are in season. Turn off lights and appliances when not in use. Limit your driving. Offset your travel. So if you're going to be traveling on a ship like this, and this ship is very fuel efficient, or you're going to be flying somewhere, I'm not saying don't fly, but there are really good programs that are audited, that are a gold standard, where they will offset your CO2. So certainly think about that. Yeah, it's going to cost you a little bit more money, but in the bigger scheme of things, I think it's worth it. Install solar panels if you live in an area where you can. Buy green energy. Even though I am not home for most of the year, I've still got solar panels. I'm almost completely off-grid. I live in a place where there's 360 days of sun, so that helps. But do think about that, because it does, for every single one of you doing something, that collective all does add up. And with that, I would like to say thank you very much for your attention.